So welcome back to Facilities Design course. In our previous lecture, we talked about the rectilinear facility location problem for single facility location in continuous space with the objective of minimizing the sum of the total distance, where the distance is measured with rectilinear distance. And for this one, actually, we have written the objective function in open form with the absolute values. And then if you remember, we said that this objective function can be separated into two for the x and y coordinates, right? And then we can solve each coordinate separately. For the x coordinate, we have a procedure to solve it, in which we order the facilities based on ascending order of their x coordinates. Okay, then we write the corresponding weights, respective weights, and then we calculate their partial sums of these weights. And whenever this partial sum first equals or exceeds half of the total weight, we say that the coordinate corresponding to this point is the x coordinate of the new facility. Okay, this is how we find the optimal x coordinate. Finding the optimal y coordinate is exactly the same procedure. Again, we order the facilities, but this time we are using their y coordinates. And then we calculate their partial sums of weights, and whenever this partial sum first equals or exceeds half of the total weight, then the corresponding coordinate to this point becomes the y coordinate of the new facility. So we identify the optimal x, y coordinates of the new facility using these procedures separately for the x and y coordinates. But sometimes we cannot place the new facility in the selected location, because in our model we haven't written any other restriction, any other constraint. So consider such a case. Assume this is our facility, okay, this is our building, and this is coordinate 0, 0. And inside this facility we have existing machines, or existing facilities, we call them, right? And then by following the procedure, we identify the optimal x and y coordinates of the new facility and assume that that optimal coordinate of x and y corresponds to this point, just at the top of an existing facility. So then placing this facility to this top of the previous facility is not feasible. You cannot do this. In this case, what will we do? In some cases, we have some alternatives, some set of alternatives saying that, okay, you can place your new facility here or here or here or here. If there are such alternatives, of course, the problem is not continuous facility location anymore, but it becomes discrete facility location. Discrete location with minisum objective and rectilinear distance. And in that case, just evaluate the objective function values of these alternatives and find the minimum. We will do an example. But if we are still in the continuous space, there are no such alternatives, then we can still solve this problem using the so-called contour lines. So in the following, we will learn how to sketch these contour lines and how to evaluate such alternatives. So let's consider this problem. Okay, so we will be solving this problem in the continuous space. It says that we are going to locate a general purpose machine tool in maintenance department. There are currently 5 machines in the department, and the coordinates of these machines, 5 machines, are given. The first machine is on coordinate x is 1, 1, the second one is 6, 2, and etc. It says that the cost per unit distance traveled between new machine and each existing machine is the same. The number of trips per day between the new machine and each of these machines 1 up to 5 are different. And they are given like this. This 10, this is the number of trips between the first machine and the new machine. So I am doing a trip 10 times. The second one, 20, 25, 20, and 25. Okay, so these are actually the given weights. And the question is, find the optimum location for the new machine such that the weighted rectilinear distance is minimized. In order to solve this, again, we will use the procedure that I summarized. We will be solving x and y coordinate problems separately. So this is the solution for the x coordinate. What do? We order the machines in ascending order of their x coordinates. So this represents the x coordinate, and we have a facility at coordinate 1, another facility in 2, 3, 6, and 8. Okay. And the weight corresponding to each one of these facilities are written also here. Then what we do, we calculate the sum of the weights, which is 100, and divide it by 2 to find the half of it, which is 50. Then in this last column, what we do, we just calculate the partial sum. For the first one, since it is the first, the partial sum is exactly equal to its weight. For the second one, the partial sum is equal to the sum of these two values. Okay, 10 plus 25. And at each time we are asking this, is this partial sum greater than or equal to the half of the sum of the weights or not? And at this point we see that it is not. Then we move to the next one. And the partial sum corresponding to here is the summation of these three weights, which is 55. And as you can see, it is greater than the half of the weights. So we say that this is the first time we exceed this half of the weights. It is important, it should be the first time. Otherwise, this 75 is also greater than 50. But we should find the first time that this partial sum exceeds or becomes equal to the half of the weights. And in this case, as you can see, the optimal x coordinate appears to be 3. Okay, so optimal x coordinate is 3, and we follow the same procedure for the y coordinate. Again, look, this order, I mean the machine order here for the y coordinate can be different than the machine order for the x coordinate, because x and y coordinates are independent of each other. So we are simply ordering the machines with respect to their y coordinates using ascending order. Okay, so we have a facility with a y coordinate of 1, another with a y coordinate of 2, and etc. And then again we list their weights, and these weights should be the corresponding weights for these machines. Okay, and then calculate the partial sums. Of course, the total sum again will be the same with the x, and half of it, which is 50, it is the same with the x1, x coordinate. And then we find the first time that this partial sum exceeds 1/2 of this total weight. And as you can see, at this point it exceeds 1/2. So we say that the optimal y coordinate is the coordinate of this machine 5, which is 4. And from this procedure, actually we know that the optimal x coordinate of the new facility will be exactly the same as one of the existing facilities, and optimal y coordinate of the new facility will be exactly the same as one of the existing facilities. But this doesn't mean that the optimal or the new facility will always be at the same location with an existing facility. It may be, it may not be. So let me give a quick example. Let's assume that we have a facility with, let's say, coordinates 5 and 8, and we have another facility with coordinates, let's say, 9 and 2. And the new facility, the statement that I told you just a second ago, says that the optimal facility, optimal x coordinate of the new facility, it can be either 5 or 9. Okay, let's assume that it is 5. And the optimal y coordinate of the new facility will be one of these two, 8 or 2. And for example, if it is 2, then the new facility can be located at 5, 2. But as you can see, this P1 and P2 is not at 5, 2. So this x is not on one of these existing facilities. But again, pay attention to the statement. There is still possibility. It is still possible that this new facility be exactly at the same location with P1 or P2. But it is not always the case. Okay, so we identified the optimal coordinates of the new facility as 3 and 4. Okay, this is optimal coordinates. Now, if we want to calculate the optimal objective function value, how we can do it? So this location over here is the optimal, is our new facility, which is located at 3, 4. And these are our existing facilities. This is P1, P2, P3, P4, and P5. So in order to calculate your objective function, you simply plug in these values of x and y into your objective function. And simply remember our objective function. We multiply the weight for P1, which is 10, and absolute value, it was x minus a1. So it will be 3 minus 1. This is the x coordinate of the new facility. This is the x coordinate of P1. Plus, let me put this in parentheses, an absolute value, y coordinate of the new facility minus y coordinate of P1. Plus, okay, this is the total distance that I am covering between the new machine and P1. And for P2, the weight is 20, and then absolute value 3 minus 6 plus 4 minus 2. And you do this calculation for all existing facilities, which is written here. This is for P1, P2, P3, P4, and P5. And at the end, we calculate our objective function to be optimal, objective function value to be 440. Okay, now let's consider the same question, the same problem with which is not continuous anymore, but which is discrete. It means that a number of alternative locations are given to us. In this case, how we can solve it? So let's assume that the previous, we are still continuing with the previous example. Okay, this was the optimal x coordinate, but it is not possible to locate your new facility to this coordinate. But you are given these alternatives. Either it will be on 3, 5 or 4, 5 or 2, 4. Which one is better? The question. Okay, which one we should locate this new facility? Actually, what you need to do is you need to calculate your objective function value using these 3 coordinates separately and identify which one has a minimum cost. Okay, so let's remember what was our objective function. minimization of the weighted rectilinear distance between the new facility and the existing facilities and their sum. So for the first candidate, which is coordinate 3, 5, if you calculate this distance, the distance of this coordinate to the 5 existing facilities by multiplying with the associated weights, we obtain this value. Okay, this is the objective function value corresponding to this first candidate. If the coordinate is 4, 5, the second candidate, then the objective function value is this much, and for the third one it is this much. So which one will you prefer? Of course, since we try to minimize, you will select the minimum of these. Okay, so the first candidate is Q1, second choice is Q2, third choice is Q3. Of course, you will go for the first choice. But sometimes Q1, the first choice, again, in our calculation here, we just considered the distance or the cost. There can be some secondary considerations, some qualitative or quantitative considerations which are different than the distance. Okay? In this case, you can select another alternative instead of the first one. Of course, if your single and only objective is to minimize the sum of the distances, this is your optimal solution. But if you want to minimize the sum of the distances, but at the same time you want to maximize your customer satisfaction, you have some, let's say, restrictions on some of these choices and etc. When you look at their objective function value, if you see that they are very close to each other, okay, this is 450, this is 460, very close to each other. But in terms of the secondary criteria, this Q2 is much better than Q1. Then you can still select Q2 or Q3. Okay? But this gives you that if your only objective is distance, the best choice is Q1. Okay. Again, let's consider the case where you cannot locate your facility to the optimum location that you identified by the procedure. Okay? In this case, how can you find an alternative location? You can use the concept of iso-cost contour lines. Okay? By this way, you can find alternative locations, the second best, third best locations instead of the optimal solution. This procedure, this process, especially if you have a large number of existing facilities, can be time consuming. We will do some examples and you will see how we do it. Okay? But it is very easy to follow this process using a software tool like, for example, MATLAB or Mathematica, or you can use your optimization tool, Cplex, to identify your next best solutions. So we will learn a 6-step procedure to sketch the iso-cost line. But the question, what is an iso-cost line? Iso-cost means, remember from your geography knowledge or when you look at a map, you see that the heights or the mountains are represented by circles or loops that are passing towards each other like this. Okay? So what does these lines mean? For example, this line can be 100, this line can be 200, this can be 300, and this can be 400. So this shows you the height of overall this line or overall this loop. So wherever you go on this loop, its height is 100 meters, wherever you go. Or for this one, wherever you go, its height is 200 meters. So since the height is equal everywhere on this loop, it's called ISO. ISO is a prefix that means identical, equal. And for our case, what we try to do in facility location, we try to minimize the cost. So for that, we will be sketching the ISO cost lines, okay? The lines that have identical cost values. Okay, so we will be using this procedure or learning this procedure, how to sketch these ISO cost lines. And when we have those ISO cost lines, then we can use those as identifying or determining the alternative locations other than the next best location. We will be doing or learning this on an example. So the first step of the procedure is this. Plot the locations of the existing facilities and designate the weights associated with each. Remember, in our example problem, we had a facility in coordinate x coordinate 1, 1. Okay? Then what we do is, okay, let's assume that this is our coordinate system. This is point 0, 0, and 1, 1 is this. Okay, this is the first facility, P1. And its coordinate is 1 and 1. And the weight corresponding to this first facility was 10, I guess. So we write the weight here and here as well. Then we have facility P2, let's say. Again, we write it is X and Y coordinates and their weights. So the first step is plotting the locations of the existing facilities. Let me show it for our example. After this cleanup, yes. So for our example, the plot is something like this. We have P1, facility 1, it is in coordinate 1, 1, and its weight is 10. P2, 6, 2, and its weight is 20. Okay, P5, P4, P3. So we plot the existing facilities in the coordinate system. Okay, the second step of the procedure is to draw vertical and horizontal lines through the coordinate points for the existing facilities. Okay, let's see what it looks like. So remember, our first facility was on coordinate 1, 1, and we are sketching a vertical and a horizontal line passing through this coordinate. The second facility was location at 6 and 2, so we are sketching horizontal and vertical lines. So just ignore these lines over here. There is no line passing through 4. It is a gray one. Only focus on the bold lines here. Okay, the bold lines are the ones that are passing through existing facilities. For example, this one passes through here and here. This one passes through here and here. By the way, at this point I need to make a remark. So let's assume that in an example we have a facility at coordinate 1, 1 and another facility, let's say P5, at coordinate 1 and 8. Okay, 1, 1 is here and 1, 8 is here. And when we sketch these two, as you can see, the same vertical line passes through coordinate 1, this one. And actually, it is what you need to do, nothing else. But in the next step, we will be writing the weight corresponding to this coordinate. And when we are writing the weight here, we will be adding the weight of this facility plus this facility and writing it here. Otherwise, the same procedure, you will follow exactly the same procedure. And we will solve examples and it will be much clearer. Okay, this is step 2, drawing vertical and horizontal lines through the coordinate points of the existing facilities. The third step is to sum the weights for all existing facilities having the same x coordinate. This is what I mentioned. Okay, same x coordinates, and enter the total at the bottom of vertical line passing through that coordinate, and perform similar calculations for the y coordinate. So let's see. In our example, remember, for this one, this vertical line, okay, it is passing through this point, this facility, which was P1, and for P1 the weight was 10. So we write weight 10 here. For this line, okay, there is an existing facility here, and we write its weight here, 25. Another existing facility, only one, and we write its value. If there is more than one existing facility on the same line, as I said, for example, another one here, another one here, so there can be 3 more, even more facilities on the same coordinate, then the weight over here that you are writing will be the summation of the weight of this one plus this one plus this one. Okay? So in this step we simply write the weights corresponding to all vertical lines just at the bottom of the lines, and similarly for horizontal lines to the left of the lines. Okay, this 25 is the weight of this facility. This 20 is the weight of this facility. Step 4 of the procedure says that, okay, calculate the net pull. Okay, it is pulling our optimal, let's say, facility. So where is it pulling? Calculate the net pull for each candidate x coordinate. So pull to the right is negative and pull to the left is positive. And do the same for y coordinates. Okay, it seems a little bit confusing, but actually not. Again, let's repeat with our example, and let's have a look at this example and find the net pull values. Okay, consider this facility or this this vertical line. Okay, then to the left of this vertical line, are there any weights? To the left of this one, are there any weights? And you see there are no weights here. There are no vertical lines, so there are no weights listed towards the left of this one. What about to the right of this grid? So consider this grid here, this row, this column here. To the right of this column, are there any weights? Yes, 10, 25. So let me write this 10, 25, 20, 20, 25. They are all left of this column, right? To the right of this column. Then it says that the pull to the right is negative. Okay, this one pulls this to the right. And since it is to the right, it is minus 10. This one also pulls it to the right. And since it is right, again it is negative. Then this one tries to pull it towards right, and it is negative therefore. So what do? We add up all these weights that are pulling to the right. So 10, 25, 20, 20, 25, when you add up them, it makes 100. And since it is pulling to the right, it is minus 100. And we write that value to the top of that column, minus 100. Okay, the next one will be more instructive. Let's look at the next one. Consider this column over here. How many weights are there to the left of this column? Or what are the weights to the left? Okay, this is the weight to the left, which is pulling this column towards left. What about the right one? Okay, this is to the right, this is to the right, this is to the right, and this is to the right. And these are pulling that towards right. Okay, pulling towards right has a weight of, has a sign of negative, and pulling towards left has a sign of positive. Then just add up these values. 25 plus 20 plus 20 plus 25, which makes 90, but it is minus 90, negative 90. And this one is plus 10. Minus 90 plus 10, it makes minus 80. So this minus 80 is calculated in this way. Let's continue. We need to find all these net pool values for each of the columns. Okay, for each of the columns. For the next one. Okay, next column is this one. To the left, I have these 2 weights, and to the right, I have these 3 weights. These are negative and these are positive. Okay, so 20, 20, 25, negative, plus 10, 25, it makes minus 30. Do it for the next one. Again, our candidate is this. To the left, I have these weights, which have plus sign. To the right, I have these, which has a negative sign. And the net value is plus 10. So the sign is very important, whether negative or positive, it is very important. Okay, so for each column, we do this thing. But we don't stop. We repeat the same thing for each row as well. What do I mean? So let's have a look at this one. Okay, this is the first row. And now, instead of looking left and right, we will be looking bottom and up of this row. So how many weights, or what are the weights below this row? There are no, it is 0. What about the ones that are at the top of this one? How many up? There are, all weights are up, which sums up to 100. But similar to the previous case, we said that pulling towards right has a negative weight and towards left has a positive weight. And here, pulling down has a negative weight and up has a positive weight. Up has a negative weight and down has a positive weight. Since up has a negative weight, so this is negative. And therefore, for this row, the net pull is minus 100. We are writing it to the right of the row. Okay, exactly the same procedure, but you need to be careful about where is negative, which side is negative, which side is positive. So let me give another example. For this row, what are the weights to the bottom of this one? These 2. And they have positive weight. And the ones that are up at the top of these, they have negative weights. And when you add up these, the net value appears to be minus 40. So we do this for each one of the rows. Okay, so this is step 4 of the procedure. Then the next step. Okay, these are the calculations, how we calculate. Actually, I explained them in detail. And in step 5, it says that isocontour lines designate movement that does not change the value of the objective function. As I said, it has the same cost value. An isocost line has the same objective function value. Then, let me show on this example, when you focus on the square or rectangular areas, which we will call grids, that are enclosed by horizontal and vertical lines, you see we have these rectangular shapes. And at each rectangular shape, you see we have an associated pull to the right and to the to the right here, and right or left here, and up or down here. Okay, the net pull values to the right or left is given at the top, and up or down is given at the right of this one. Now, focus on this one. Let's concentrate on this grid. Okay. In this grid, the net pull is plus 10 here. What does it mean? It says that there is a net pull to the left. Plus means to the left. And here we have 100 plus 100. It means that there is a net pull to down. Okay, this means down. Then any point at this grid will be, let's say, pulled to the left by 10 units and down by 100 units. And with respect to this one, actually it will be going in this direction like vector sums. And the slope of that movement will be simply this value minus 0.1, which is calculated by dividing 10, which is this, to 100, which is this, and taking the negative of that one. Okay, so this value over here is the slope of the movement, let's say, in this grid. For example, let's see another one, this one. It says minus 5. Why is it minus 5? Because it is 50 divided by 10, because 10 is the row value and 50 is this column value, and don't forget the negative sign. So for each grid at this step, for each grid we calculate the slope values. Okay, for the first one, when you use minus 100 divided by plus 100 and take the negative value, you end up with a slope of plus 1. Okay, this is step 5. Calculate the slope at each grid using the net pull values of the columns and the rows, but they divide the weight at the top to the weight on the right and take the negative of that. Don't forget this negative sign, it's important. The last step is to sketch the isocontour lines. Okay, the isocontour lines may have different shapes. They can be symmetric mostly, but sometimes they are not symmetrical. And this is an example of the isocoastline for the given example actually. And what does it mean? Look, this shape inside here has a cost value everywhere on the line. So if you locate your facility here, it will be exactly with the same cost with this facility that you locate here or here or here or here. Anywhere on this loop or on this contour line have exactly the same cost. But these are different than the facilities that are located to an outer line, outer loop. So these green ones will have a different cost than the red ones. And of course, as it is expanded outwards, the cost will be increasing. Okay, the cost of red loop is less than the cost of the green one. It is less than the cost of an outer loop, and etc. Okay, but the question, how did we sketch these contour lines? In the previous example, we just identified or determined the slopes. Then how can we find or how can we sketch these contour lines? So I will be explaining that in another example, but the main idea is this. You just start with a point on the coordinate system, any point. Let's say this one, okay? This is your starting point. And then from this one, you can go either to this or to this grid, whichever you like, and look at the slope here in this grid. So if that slope is, for example, -7, then starting from this coordinate, you will move with a slope you will sketch a line with a slope of -7. And remember, in the coordinate system, whenever a line is a positive slope, it means that it has a shape like this. Whenever it has a negative slope, its shape is like this. Okay, so these are negative slopes, these are positive slopes. So this one, since it is negative, it will be going in this direction. And then identify the next point, the next coordinate that this line intersects with the border of the grid. Assume it is this one. Actually, it is this one. Okay? And then it means that from this grid, which has a -7 of slope, I'm entering to this grid, and let's say it has a +2 slope. Then, starting from this one, I will be moving using this slope +2 until I hit the border of the next grid. And identify this coordinate and then move until the next point and then identify that coordinate. And when you continue till to the end, since it is an isocoastline, it must always return back to exactly the starting location. Okay? It will always return back to the starting location and close the loop. If you do a mistake in these calculations, then you will not be able to find or close the loop, and your isocoastline may go somewhere else, which is not meaningful. Okay, so this is the procedure, and I will solve an example in our next lecture, but let's take a break.